what up, what up? Today in AP Precalculus land, we're going through 4 sections. They all talk about rational equations, rational. That means fractions. So let's get right to it. First thing that we're going to talk about is zeros, asymptotes, and end behavior. When you graph rational functions, you're expecting weird things to happen, okay? Things that look something like this. And you're like, what the heck is all of that? And it looks sad because it is sad. So you're expecting strange things to occur, things crossing the x-axis, things non-existing. That's where all of this info comes into play. First things first, let's talk about zeros. Now, a zero is found whenever you take your f of x or your y, and every single thing that we look at is going to be from the point of view that the denominator is q of x and the numerator is p of x. So if I'm finding the zeros, you're pretending the y is 0. And the way you find the zeros is you set the denominator, who cares, and set the numerator equal to 0. And if you're like, well, wait, what do you mean who cares about the denominator? Look, baby. If that was 0 and you multiply both sides by q of x, what's going to happen to q of x? That's going to happen to q of x. You are gone. We don't care. So chances are the numerator is going to look like a polynomial, or maybe it already looks something like this, and you can do zero product property on it. So that's how you find the zeros. You look at the numerator, factor it if you must, and see if you could do zero product property to find out where your zeros exist. So that's zeros. What are asymptotes? Asymptotes is going to be wherever your graph explodes. Now, the only thing that makes an equation that's also a fraction explode is whenever the denominator is undefined. Undefined means, is there a number that you can plug into the denominator that gives you 0? So asymptotes exist at these moments where the denominator is equal to 0. Now, asymptotes, again, and if I were to draw like a similar picture that I drew before, I don't know why I'm dashing these, asymptotes live at a vertical line where the explosion takes place. Now, since this vertical line is a vertical line, the equation of a vertical line is going to be x equals some number. So if I gave you something like x minus 3, blah, 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 equals 0, then you would do the opposite and say that number is 3. That is where an asymptote exists. Now, what also could possibly exist is a horizontal asymptote, which means a line that goes through there where my graph will neither touch it horizontally. That's where end behavior takes place. So the end behavior takes place when we're talking about my limit. So what's my equation doing when x is approaching infinity or negative infinity? Okay, now there's 3 different cases that we're going to look at, and in all of those cases, they're all going to be different. Okay, so I'm not going to just come up with some blanket example. All I know is when my limit is approaching infinity, that means this blue line is going to approach this red line but never officially touch it. Same thing on the left. So me trying to say it's always going to be this, we don't know. That's part of the fun. So let's look at possibility number 1. What if I give you an equation where the numerator and the denominator have the same exact degree? What if the numerator and the denominator have the same exact degree? I'm going to put up some, pictures of cases like this, starting with, a regular x something over x something, and then move my way up. And as you can see, explosions take place. You can see my end behavior doing something to the left, my end behavior doing something to the right. Lots of stuff going on. But like the main idea of a graph is going to look something like this. Or maybe it looks something like weird like this. But what's going to happen is the left and the right are going to approach the same area. And in certain cases, we might have things going in. I'm jumping the gun. I'm saying too much. What matters is the asymptotes. I thought I misspelled that. I spelled that right. It's a terrible word. The asymptotes. Again, the asymptotes exist whenever the denominator is undefined. So if I give you just a regular guy like x minus 4 over x minus 3, okay, and if that's wrapped in parentheses and you have a bunch of parentheses over here and a bunch of parentheses over here, as long as you have the degree on the top being the same as the degree on the bottom, even if that's not the case, the vertical asymptotes are going to be whatever makes the bottom 0. So in a case like this, x equals 3 is going to be a vertical asymptote. Okay? Now, I thought a simp was somebody who was trying to get on my Instagram and get my attention. I'm just joking. That doesn't happen. End behavior. Now, this is where we're talking about limit stuff. Okay, so let me give you just a very, very, very basic example of something where the degree on the top is the same as the degree on the bottom. And let's just say x is approaching regular old infinity. So if I said x squared plus x minus 6 over x squared plus 5x minus 9, and you're like, I can't factor the bottom. How am I going to find the end behavior? Simple, don't worry about it. This is what you do. Whenever you're being asked to find the limit of a polynomial over a polynomial, take the leading term in the numerator, take the leading term in the denominator, and forget everything else. So our main focus is going to be x squared over x squared. And you might be thinking, well, that simplifies nicely to 1. And that is true. And so let's take the limit as x approaches infinity of 1. Usually if you're being asked to find the limit as x approaches anything, you just plug in that number for x. There's no x to plug in. So my answer is just 1. And if you're thinking that's just a bit too easy, give me another. Fine. Limit as x approaches negative infinity, so let's flip it around, of 3x squared blah, blah, blah over regular x squared blah, blah, blah. We don't care about the blah, blah, blah. So what happens is this simplifies, and the limit as x approaches anything of 3 is going to be 3. So to find the limit, whether it's positive or negative, the limit, whether it's positive or negative, is found by doing the leading term divided by the leading term. When the degrees are the same, they cancel each other out, and whatever number is left over is your answer. Now, what I just said, as far as the way you find the limit of a polynomial over a polynomial, you just take the leading term. That's the case for all of them. It's the case for every single one. But in the case where the degrees are the same, it's always going to be a constant number, a number found by doing the leading coefficient divided by the leading coefficient. So that's when the degrees are the same. What if the degree in the numerator is bigger than the degree in the denominator? Okay, so something like x cubed over x. What does it look like then? Well, I'm going to throw some pictures up on the board, and as you can see, not on the board, on the screen, and as you can see, you know, things kind of get a little curvy. Okay, curvy's dreamland. And some of the problems that we get, and I think the first picture that I showed you looked something like this, where it kind of looks like a sideways hyperbola thing, and you're like, what is that? What is that? And if you're wondering, all right, well, maybe I can squeeze in a vertical asymptote there, but I certainly can't squeeze in a horizontal asymptote. I'll show you what I mean. Vertical asymptotes are exactly the same. Vertical asymptotes are going to behave exactly the same. You have x plus 3 on the bottom as a factor somewhere. All right, x equals negative 3 is going to be a vertical asymptote. Nothing to think about, bada bing. Now, what occurs here is we are going to have what's called a slant asymptote. A slant asymptote, okay? So if I give you a problem just like this, and I'm asking you to find what is, like, let me give you this exact example. X squared minus x minus 6 over x plus 4. And I asked you to find the slant asymptote. The way you find the equation to a slant asymptote is you do polynomial long division. Yeah, I said it. You could do synthetic division, but I prefer polynomial long division, so let's set it up. X plus 4, x squared minus x minus 6. Your answer, ignoring the remainder, is going to be your equation for the slant asymptote. One more time. your answer, ignoring the remainder, is going to be your equation for a slant asymptote. So let's do some long division. X times what is x squared? X times x is x squared. Put an x up there. Now we take that x, we multiply it by the dividend, and we do x times x is x squared. X plus 4x, or times positive 4 is plus 4x. And then we subtract the entire row here. Okay, so you are now negative. X squared cancels out. Negative x minus 4x is negative 5x. Drop down to negative 6. Funzo. X times what is negative 5x? Minus 5, of course. Take that negative 5, multiply it to this guy, so negative 5x, negative 20. Subtract the entire thing, which means flip the signs. You go away. We have a remainder of who friggin' cares. The equation of my slant asymptote is x minus 5. All right, I had to do a location change because my kids started barging into the dining room. Children, can't live with them. There's probably an end to that sentence there. End behavior, speaking of end behavior is what happens as my limit seems to approach something. Well, it all completely depends on what you have as far as the equation, but don't let it bother you too much. What we see with pictures like this, okay, with graphs like this, is this picture should keep going like that way, and this picture should keep going down that way, okay? So what we can expect is a similar thing. So if I give you like the limit as x approaches regular infinity, here, let me quick do this. Let me maximize my screen again. As limit approaches, or x approaches infinity, of something like negative x to 4x to the 4th over x squared. All right. Well, clearly the numerator is greater than the denominator as far as degrees go. You're going to, again, and by the way, plus stuff, minus stuff, blah, 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 blah. Let's pretend that you're the leading term and you are the leading term. When you're the leading term, simplify as much as you can. Expect the numerator to dominate the denominator, and you get negative 4x squared. Now, if I were to take this and plug in infinity to negative 4x squared, what's going to happen is I get negative 4 times infinity squared. Infinity times infinity is infinity, and multiplying that to a negative number is going to become negative infinity. So very similarly to the last slide, what we do is we take the leading terms, simplify it, expect the x to be larger in the denominator and the numerator, and then plug in infinity, and you're either going to get positive infinity or negative infinity. It's always going to be the case that way. And if I gave you something like, let's find the limit as x approaches negative infinity of, let's just say, x to the 5th over x. You simplify that, you get x to the 4th, you plug in negative infinity to the 4th, and negative infinity times negative infinity times negative infinity times negative infinity is positive infinity. So you're going to get one of the infinities whenever your numerator is greater than the denominator. So last but not least, what if the denominator is greater than the numerator? Okay, let me show you a bunch of graphs again. We see a lot of similar behaviors. These are probably more like when they're equal and less like, we're not expecting any slant asymptotes. We're still going to have vertical asymptotes, and the vertical asymptote stuff is still going to exist whenever you have something on the bottom. So, even if I have nothing at top, a 1 at top, you still have, like a vertical asymptote living at 3 in a case like this. Now, my end behavior, if my denominator is bigger, let's say I had the limit as x approaches infinity of 3x to the 5th over x to the 9th. Okay, you simplify that as much as you can, so 3 over x to the 4th. Now, let's make sense of what's about to happen. My x is greater than, in the denominator, than the numerator. As x gets larger, like let's just pretend like we're testing this out for the first time ever. Let's plug in 1. I get 3. Let's make x bigger. Let's plug in 2. Okay, 2 times 2 times 2 times 2 is 16. That 3 just became point something, like something that's near 0. If we were to plug in 5, okay, I now have 3 over 625. That number, 3 over 625, is almost 0. If I plug in 10, I now have 3 over 10,000. That number is 0. This whole number is almost 0. So anytime my x gets bigger, my number as a whole gets much, much, much smaller. And this guy is 3 10,000ths, 0.0003. So when I only plug in 10, imagine what would happen if I plugged in like 1,000. Our number is basically going to be 0. So whenever we ask for the limit as x approaches either infinity, positive infinity, or negative infinity, and it doesn't matter what we have up here. So if I add x to the third up here, blah, 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 x to the fourth down here, blah, 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 blah. Whatever's going to happen is whenever your x is more dominant in the numerator, the denominator, you are always going to hit 0 when your limit approaches either infinity. So that's the end behavior. Okay, when the degrees are the same, the limit as x approaches infinity is going to be the ratio of the leading coefficients. When you have a case like the last one, when the upstairs is bigger than the downstairs, you're going to head towards one of the infinities. And in this case, when the downstairs is bigger than the upstairs, you're going to head towards 0 no matter what. So before we actually start doing some examples, let's talk about wholes and multiplicity. Now, we know that if I were to do something like this, okay, we should expect crazy things to happen at 3 and 5. Well, what if I added this to it? Whenever one of your factors in the numerator is the same as a factor in the denominator, what happens is the behavior of the graph is going to be as if these were crossed out. So the graph behaves like 1 over x minus 5. However, x still can't be -3. So regular 3. So what's going to happen is you might have a graph that looks something like this, but at +3 you have a hole and it keeps going. Okay, so whenever the numerator and the denominator are exactly the same, expect a hole to exist there. Even though the graph acts as if it didn't exist in the first place, we're still not allowed to plug in 3 because of the original problem being what it is. Now, let's just say that somewhere in the problem, I have something like this, x minus 2 squared. That implies multiplicity. Now, what we had up here is we were expecting things to go wacky at regular 5, which makes my picture not accurate at all. That hole should have been over there, but you get the idea. This wackiness happened at x equals 5, mainly because x is not allowed to be 5. However, when you have an even multiplicity creating an asymptote, what's going to happen is these guys go up in the same direction. So at 2, these guys are going to go up in the same direction. Maybe they go down in the same direction. It all depends on what's going on up here and anywhere else. But when the multiplicity is even, both lines go up or down in the same direction. Now, similarly, if I were to give you a problem like this, right, where I have multiple multiplicity things going up here, and then multiple multiplicity things going on down here. Okay, the same rules apply. It takes on the behavior of something like this, and we still see action like this happening on our graph. Okay, so rationals are weird. They give you weird graphs. And we obviously have a lot going on with these types of problems. So I think we can now start doing some problems. All right. Just kidding. Working backwards. Lots of problems are going to give you something like this. let me give you something where the degree of the numerator is 2 and the degree of the denominator is also 2. I don't know why I put 3 there. And let's just say that there is a vertical asymptote at 3 and a whole at 4 and a 0 at 5. We can create a rational function. If the vertical asymptote is 3, that means it explodes at 3. Now, what's a factor going to look like if it explodes at 3? X minus 3, because if I plug in 3, 3 minus 3 is 0. If a whole exists at 4, that means I have the same exact thing up here that I have down here, and all the action happens at the opposite, x minus 4. If a 0 occurs, that's going to happen when a factor in the numerator gives you a 0, so x minus 5. So that would be an example of something like that. So now I think we can go over a few problems. All right. So based off of what we learned, f of x equals numerator, denominator. The degrees are the same. I have a factor with an x, a factor with an x, so x squared upstairs, a factor with an x, and a factor in an x with an x squared downstairs, x squared, everything's the same. Find the zeros. We find the zeros by taking the numerator and setting that equal to 0. So x minus 5 times x plus 9 equals 0. 0 product property. X equals the opposite of x minus 5 and the opposite of x plus 9. Okay? Pretty simple. The vertical asymptotes. Since nothing upstairs and downstairs repeats, my vertical asymptotes exist at the opposite down here. So where does x plus 3 and x plus 4 equal 0? Well, the opposite of plus 3 and plus 4, which one of my vertical asymptotes is going to be negative 3, and the other vertical asymptote is going to be the equation x equals negative 4. I'm writing it out like this because they're both equations, whereas these guys are x values. What is the horizontal asymptote? Well, the horizontal asymptote exists at the end behavior. So by doing C, we do D. And for some reason, I have a second C. Great. What is the horizontal asymptote? Well, let's answer first C and D at the same time. The way we find the horizontal asymptotes is the same way as finding the limit as x approaches infinity. What you need is the leading term. Well, I don't have a leading term, but there's a shortcut. Always take the leading term in each factor and multiply them together. That will give you the leading term for the numerator. Do the same thing. Multiply the leading term of each factor. That will get you the leading term here. I don't care about anything else. So my concern is x squared over x squared, which becomes 1. So what happens when we plug infinity into x? Well, there is no x. I just get 1. So the limit as x approaches infinity is 1, which means my picture, whatever it looks like, is going to end up flattening out at 1. Okay, and the same way. So a horizontal line that flattens out at 1 is going to be the equation y equals 1. Okay, so we killed 2 birds with 1 stone, and we're about to kill a third, because what is the whole? Well, the whole exists when you have a factor in the denominator that's the same as the numerator. We don't, so there is none. Nowhere. Fun. Love these. Love them. Love them so much. Find the zeros. All right. Now what I have to do is I have to, looks like factor everything out. So I'm going to pull out an x upstairs. So that leaves me with x squared minus x minus 6. In the denominator, I can factor that, difference of squares, x plus 4, x minus 4. I can continue factoring the top because this is going to factor out to x minus 3 and x plus 2 over x plus 4, x minus 4. All right. Find the zeros. My zeros exist wherever the numerator is set equal to 0. So x is going to equal 0, x minus 3, positive 3, x plus 2, negative 2. Find the vertical asymptotes. Nothing upstairs and downstairs repeat. Nothing. So my vertical asymptotes are wherever my denominator is set equal to 0. So x minus 4. So that's going to be negative 4. X equals negative 4. And also the equation x equals positive 4 because it's the opposite of these numbers in here. Find the slant asymptote. The slant asymptote, whenever your denominator is greater than the numerator, is going to be when you divide that from that using long division, polynomial long division. So let's do polynomial long division. X squared minus 16 divided by x cubed minus x squared minus 6x plus 0. And if you're wondering, do we have to put the plus 0 there? You do. I think you do. Maybe I'm wrong. We'll find out. X times what is x to the third? I'm sorry, x squared times what is x to the third? X squared, oh, you know what I forgot? Oh man, this would have derailed the whole thing. I'm missing an x here, so I have to write out x squared plus 0x minus 16. That would have ruined everything. Here I am talking about, do I have to do this? And I forgot about doing this. Shame on me. X squared times what is x cubed? X squared times x is x cubed. Multiply x to everything. X to the third, 0, negative 16x. Subtract this guy, which means flip the signs and bring it down. You go away. Negative x squared minus 0x squared is negative x squared. Negative 6 plus 16 is positive 10x. Drop down the plus 0. Okay? X squared times what is negative x squared? Negative 1. Negative 1 times x squared is negative x squared. Negative 1 times 0 is 0x. Negative 1 times negative 16 is 16. Flip the signs on everything because you're subtracting. So plus, minus, minus. You go away, and you're going to be some remainder. Now, who cares? Who cares? Because this guy gives me the equation of the slant asymptote. So my equation of the slant asymptote is y equals x minus 1. Find the limit as x approaches infinity. So I'm going to go back to the original problem. I'm going to pretend you guys don't exist. So the limit of x cubed over x squared, okay, is the same thing as saying the limit as x approaches infinity of x. What happens when you plug infinity into x? You get infinity. So I'm expecting this picture to basically, I don't even want to draw it. I'm going to pretend. X might, probably something like this without drawing it. Okay? Oh, that's going to look so bad. No, that's not even right at all. Yeah, see, I don't want to do it. I don't want to do it. I don't want to do it. Let's just pretend I was drawing a road. All right, next problem. Oof, gross. All right, so I have x to the b times x plus 2 times x minus 4. Find an integer b that would give f of x a horizontal asymptote of y equals 1. Okay, so we have to be careful here. Horizontal asymptotes live where your limit approaches infinity. Okay, so if I were to give you an example like this, if P was bigger than Q, okay, so there's three situations where P is bigger than Q, Q is bigger than P, and P equals Q. So let's use common sense. If P was bigger than Q, that means this guy is greater than that guy, which means that has more x's than that, which means I'm going to approach one of the infinities. So this is not the option that we would use. When Q was bigger than P, that means I would have like x to the fifth, and maybe up here is x squared, and this approaches 0. So in a case like this, I need P equal to Q. So I need P equal to Q. I have one leading x, another leading x, so that's 2, and my leading coefficient down here is x to the 5th. So in order to make this match up with that, I have 2 x's up here, I don't know, has to match with 5 x's down here, b has to be 3. Because when that's x to the 3rd, and I multiply all this out, I have a leading coefficient of x to the 5th, which matches up with x to the 5th. Great. Find any vertical asymptotes. Well, let's bring out x cubed. That leaves me with x squared minus 9. By the way, I'm factoring out the bottom, the denominator. Okay, I can factor that further. X to the 3rd is going to equal, is going to be multiplied to x plus 3, x minus 3. So times x plus 3, x minus 3, and that gives me 3 vertical asymptotes. Triple multiplicity at 0. The opposite of 3 is negative 3. And the opposite of negative 3 is, ooh. And look at me being foolish. Since I pulled out an x to the 3rd and I made upstairs x to the 3rd, I have x to the 3rd up here and x to the 3rd down here. Find any holes? Holes exist at x equals 0. I don't have any horizontal vertical asymptote at 0 because since I have x cubed upstairs and x cubed downstairs, they cancel each other out. And the whole thing here ends up having a behavior of an equation like x plus 2 times x minus 4 over x plus 3 x minus 3. And since I had x cubed out here and x cubed out here, my holes exist there. And I don't have a vertical asymptote at 0. Whew. Oh, dodged a bullet on that one. Find the limit as x approaches infinity. All right, well, multiply u to u and multiply u to u, and I get x squared over x squared, which equals 1. Phew. These problems are tricky, and you need to be a little careful on them, because I was not careful with this guy right here. This is stupid because I created these problems. I should be a little bit more careful. Rewrite f of x as one fraction. Ooh, I hate these. So what we're going to do in order to rewrite it as one fraction is we're going to, let me rewrite the first fraction, give myself some space. I need a greatest common denominator. Nothing in common. So I just need to multiply this guy by x plus 1 over x plus 1. And I need to multiply this guy by x minus 4 over x minus 4. I'm going to keep the bottom factored. So x plus 1, x minus 4. Upstairs, if I do distributive property, I have 2 times x, 2 times 1, negative 5 times x, be careful, negative 5 times negative 4. And then these guys combine to make negative 3x plus 21 over x plus 1x minus 4. All right, done. Find the x values that make f of x equal to 0. Well, if f of x was equal to 0, this is the same thing as me finding the zeros. So who cares what that is? Because I'll just multiply that to 0 and it'll go away. So what I need to do is do negative 3x plus 21 equals 0. Subtract 21, so negative 3x equals negative 21. Divide by negative 3, and the only x value that would make f of x equal to 0 is 7. Okay. I'm just doing the math over here. Oh, it's gross, but yeah, that works. Find the limit as x approaches infinity. Okay, so if I were to look at this guy here, I have negative 3x as a leading coefficient. Okay, this has to do with u. Negative 3x as a leading coefficient over x times x, which is x squared. That simplifies out to negative 3 over x. And as x increases, as x gets larger, we are going to hit 0. So the limit as x approaches infinity is 0. Where is f of x undefined? At 4 and negative 1. That was kind of friendly. It's kind of easy one finally. Until we hit this. Estimate the rate of change on the interval negative 1,000 over 1,000. Well, hold on. If the limit approaches infinity is 0, that means my graph is going to be like way over here at right around 0. So like if I were to plug in like 1,000, I'm going to get 0. Similarly, if I were to go to negative 1,000, I mean, no matter which infinity I plug in, this is still going to be 0. So this is basically going to be 0. So the rate of change would be, what's the difference between 0 to 0? Oh, that's why it says estimate. Oh, I should have known. Oh, me, creating fun problems. Yeah, the last thing you want to do is plug in 1,000. But even if you did, let's just have fun and say you did. If I plugged in 1,000, I would get 2 over really big number minus 5 over really big number, basically 0 minus 0. And if I plugged in negative 1,000, I would basically get 0 minus 0. And so 0 minus 0 is 0. Not fun. That's fun. Multiplicity everywhere. Find any vertical asymptotes. Well, ooh, okay. Okay. I can do this. Now, I have, let's ignore that problem for a second. Find any holes. See how these guys are the same exact denominator? Holes are going to exist at negative 4. Now, here's the thing. It's not going to exist at 1 because what's going to happen at 1 is since I have more x minus 1s in the denominator that I have in the numerator, it's going to take on the behavior of 1 over x minus 1 to the third. Okay, so it's going to take on that behavior, not giving me any holes there. And so I'm going to have a vertical asymptote at x equals 1. These guys crossed out. That's what gave me holes. They completely crossed out. You crossed out and left me with 3, and the whole thing ends up looking at that like that. So holes are at negative 4. Vertical asymptotes are at positive 1. So my equation now looks like this, where I'm not allowed to plug in negative 4 or 1. Since I have a much more powerful denominator, all right, if I were to take this and multiply that to itself 3 times, it follows the behavior of 1 over x cubed, okay? And when you multiply, or not, don't even do that. When this number gets much, much, much bigger, whenever you have 1 over or 3 over or number over x to the who cares, it's always going to equal 0 because in this case, the denominator is greater than the numerator. Find the zeros. Ugh. All right, well, let's factor that. I can bring out a 2x, and that's it. That leaves me with x squared plus 4x plus 4. Ooh, a perfect square trinomial over difference of squares, x minus 3, x plus 3. So now you become 2x, x plus 2 times x plus 2, which is x plus 2 squared. Multiplicity. Multiplicity. This becomes x minus 3, x plus 3. So nothing fancy happens. No holes. So I don't have to worry about that like I saw in a previous problem. Find the zeros. Well, the zeros exist whenever the numerator is set equal to 0. So what happens when 2x is equal to 0? Divide by 2, you get 0. X plus 2 is equal to 0. Subtract 2, you get negative 2. find the vertical asymptotes. That exists whenever the bottom is set equal to 0. So vertical asymptotes are the equation x equals 3 and the equation x equals -3 because they're the opposite of that. Find the slant asymptote. Well, since this guy's bigger than that guy, I'm going to have myself a slant asymptote. So let's do x squared minus 9. But I have to remember 0x minus 9. Not going to make that mistake again. And I'm going to divide the original guy here. 2x cubed plus 8x squared plus 8x plus 0. X squared times what is 2x cubed? 2x. Okay, multiply 2x to this whole thing. 2x times x squared is 2x cubed plus nothing, x squared. Minus 18x. Okay, flip the signs. Minus, minus, plus. You go away. You become 8x squared. You become, that is a minus, so it became a plus. I was just making sure I did it right. 26x, not that it matters, plus 0. X squared times what gives you 8x squared? Plus 8. 8 times x squared is 8x squared plus 0x minus 72. Not that it matters because you go away. I don't care about remainders. The slant asymptote is the line y equals 2x plus 8. All right. I have to take another break. This last one, I may have included one that's just a bit too bonkers, but we're going to do it anyway. I'm not sure if you'd see one this crazy on a no calculator portion, but like I said, let's give it a shot. I'll walk you through everything. I'm now asking you which part of this graph is going to be positive. So let's just try to break it all down. Okay, let's just try to break it all down. Let's find out where the limit is, all right, as x approaches -infinity. And let's find out what the limit is as x approaches positive infinity. I'm going to try to put together a very marginal graph to help me figure stuff out, see what happens. Remember, when you're trying to find the limit, you're going to take the leading term over the leading term. Nothing else really matters. Okay, so in both of these cases, the only thing that really matters is the fact that I have 2x cubed over x squared, which simplifies to 2x. If I plug in -infinity, 2 times -infinity is -infinity. Similarly here, 2x. If I plug in infinity, it's going to be infinity. So I know that all going to the left, this guy is heading downward, going to the right, this guy is heading upward. What else do I know? Well, zeros are at 0 and -2. Now, I put a B up there before I started recording for some reason because since the multiplicity at -2, where is it? There you are. At -2 is 2, it's going to bounce. So action happens at the zeros, and what's going to happen is a bounce here. Now, what else do I have? I have stuff going on at asymptotes, which occur at -3 and +3. So let's recreate, okay, let's recreate a very possibly inaccurate graph of what this is going to look like. Action happens at -3, -2, 0, and 3. So -3, -2, 0, and 3. That's where the action happens. Okay. Now, my zeros are at -2, which means whatever happens, nothing crosses the x-axis until 0 and -2. -3 and +3 are asymptotes. So since my limit as x approaches -infinity is also -infinity, and I have a change happening at -3, I have an asymptote at -3, this guy is going downward. But what also happens is this guy becomes an asymptote. Now at -3, I have a regular looking asymptote, no multiplicity. So since there's no multiplicity, this guy is going to reappear up here. At -2, I bounce off. So I'm going to go to -2 and bounce. I'm going to come back up. At 0, I go through. And then I'm going to go downward. At +3, I have an asymptote. Since the multiplicity is 1, it reappears up here. And since the limit is positive and I'm not crossing the x-axis, it's going to look like this. So let's erase all of this mess over here. Okay, sorry, long division, but I'm erasing you. And let's make ourselves a sign graph. Again, will you see a problem this crazy on AP PreCalculus in the no calculator section? I don't think so. This problem is insane. I think when I created it, I just wasn't thinking and I just made things difficult for me. Action happens at -3. Action also happens at -2. Action happens at 0, and action happens at +3. Okay? From -3 and on to the left, it's underneath, so it's going to be negative. I'm just going to write it out. I'm not going to try to draw it like I've done in the past. From -3 to 2, it's positive. From -2 to 0, it's positive. From 0 to 3, it's negative. And I accidentally erased this chunk right here. And from 3 to infinity, it's positive. I care about where this stuff is positive. So it's positive between -3 and 0, but I'm not allowed to include -2 because it hits -2. So I will say that between -3 and -2, it's positive, union. Between -2 and 0, it's positive, union. And from 3 on to forever, it's positive. Awful, awful, terrible, terrible problem. I'm sorry. But I think this is the last one coming right up. And it's not. A fractional function in the form p of x over q of x has the traits of the graphs shown below. Create a function that has a hole at 3 and a vertical asymptote at -4. All right, q of x appears to be a quadratic, so the degree is going to be 2. P of x appears to be linear, so the degree is going to be 1. All right, so let's start out with the hole. If I have a hole at 3, that means down here I have x minus 3, and up here I have x minus 3. And if it has a vertical asymptote at x equals -4, then down here I have x positive 4. The quadratic is degree 2. There's 2 x's. And the linear is degree 1. There's 1x, and I'll just throw an f of x in front of it, and that should do it. Not bad. Not bad. I like it. I can appreciate that problem. Now we're at the last one. Now, this is a calculator problem. Okay, look at it. Use the calculator to do this whole mess. So I'm going to use the calculator to do this whole thing. Find the zeros. Okay. All right, we have a crazy fraction we have to graph, so let's hit y equals and graph it. What I'm going to do is make sure that my entire numerator is in parentheses. So I'm starting out with an opening parentheses, and I have to make sure that I close it. So double parentheses here is done on purpose. My x value is right here, so click that, plus 2, close it. And then I have x minus 5, close it. And then I have a quadratic, so x is right there, squared is right there, plus 1.5x, plus 1.5x, minus 67.5, bada bing. And since I started out with a big left parentheses, I have to make sure I close that parentheses. Now the entire numerator is wrapped in parentheses. Hit divided by to create your fraction bar. I'm going to do the same double parentheses to do the numerator because I have a bunch of stuff going on down there as well. Denominator, I think I said numerator. Whatever. No one's paying to hear me speak. X minus 4. Now, don't forget to square it. That's going to give us some multiplicity. That'll show up later on. X plus 7. and x plus 2. Ooh, so an x plus 2 in the numerator and the denominator. I wonder if that'll show up. Now let's hit graph and see what I end up with. Now, our first job is to find the zeros. The zeros exist whenever the numerator is set equal to 0 and you solve. I'm factoring a bunch here, except that I didn't factor that part right there. I have a feeling that wherever x plus 2 is, it's not going to work out. Because I have an x plus 2 in the denominator, it's going to create a hole. But I expect a 0 to exist at 5. This right here is gross and it wasn't factored for me, so I'm assuming it's going to give me zeros that would be like me factoring that. So let's find the zeros. The way you find the zeros is you hit second, calc, and then either hit 2 or go down and hit enter, and then zeros. I'm expecting a 0 right there. I'm expecting the 0 right there, and I'm expecting the 0 right there. So let's go left to right. I'm going to hold down the left button, and I'm going to make sure my cursor is to the left of where my 0 should appear. So since I'm assuming it looks like it was -9, my dot is blinking in the positive y range. I'm going to hit enter. I'm going to go to the right until my y has a sign change or until I cross the x-axis, which is what I did. I know I did because it was at positive, now it's negative. Hit enter. My 0 should be in between these two areas. Hit enter again, and it gives me a 0 of -9. So then we repeat the process. Second, trace, go to 0, and we're going to go all the way to the right until we end up to the left of what appears to be around -5, give or take. It could be something different, but if I recall, one of my zeros or one of my factors was x minus 5, so I'm expecting this to be regular 5. So hit enter since we're on the left side. Let's cross sides, hit enter again. Always hit enter for guess. There's my 0 of 5. Let's do it one last time. Second trace. 0. Let's move my cursor to the right a little bit. To the right. Cupid Shuffle. Remember him? Someone told me the other day that he's in jail, and I don't believe it. Anyway, I crossed the x-axis. Let's hit enter. And by hitting enter through guess, I have a 0 of 7.5. So my zeros were at -9, 5, and 7.5. So if I look at this, the 5 makes sense. The -9 and the 7.5 must come from this gross-looking quadratic right here. And if you're wondering, well, what about that, what was it, x plus 2? Why did we go through -2? Because there's an x plus 2 on the bottom. We'll deal with that in a second. Oh, terrific. I wrote it down here somewhere. The zeros are -9, 5, and 7.5. What coordinate does a hole exist? Oh, this one's going to be fascinating. I wonder how it's done. Hey, remember a few seconds ago when I said we're going to deal with this in a few seconds? Well, here we are. What I need to do is I need to find where the hole exists. Now, I have x plus 2 on the top and x plus 2 on the bottom, which means my hole exists at -2. Now, here's the thing. You might be thinking, well, why don't we plug in -2? Well, if I plug in -2 into this denominator here, it's going to be undefined. Let me demonstrate that. Hit second trace and go to value. This allows me to find the exact value if I type in -2. So -2, enter. See how it says y equals blah? That's because there's no blah. And I did not say blah, blah, blah. I just said blah. So what I want to do is, since I can't plug in -2, let's plug in -2.001. Much better. That gives us 2.5869. So let's write that out. 2.5869. Now, some of you purists might be like, well, since we tried it one space to the left, why don't we try it one space to the right? Good idea. Let's plug in -1.999. So value, -1.999. Hit enter, and I get 2.5861. So since I got 2.5869 and 2.5861, let's settle on a final answer that is somewhere in between at 2.586 5. Oh, magnificent. Magnificent. So the coordinate is going to be -2, 2.5865 as clearly seen. That is an 8. Ugh. All right. Find the limit as x approaches -infinity. Let's find the limit as x approaches -infinity. Well, I really can't see where -infinity is, and I can't see where that's going. So let's do this. Let's create a new window where I want to see what happens at like -infinity. My x-min is at -10. That's not even close to -infinity. So let's set it to -10, 1, 2, 3, 1, 2, 3 million. -10 million, it's a pretty big number. So if I hit graph, straight line. But where is that straight line? Well, let's do the value thing again. Now that I changed my window, I can actually find out what the value of -10 million is. And when I hit enter, I get y equals 1.00000. Oh, you know what? 1.00000 is probably 1. So I'm going to go with that. Now, if you were thinking, sir, when it looked like this, why didn't you just plug in -10 million there? Because it doesn't let me plug in a value unless the calculator sees it on the screen. So I have to change my window in order to make that work. Oh, okay. I probably didn't need a calculator for that, but, you know, here it is. It's 1. And find the limit as x approaches 4. Well, that's a new problem. I wonder how we could use a calculator to do it. All right, last but not least, let's see what happened when my limit hits 4. Now, here's the problem. Problem number 1. I can't plug in 4. Why? Well, x minus 4 lives in the denominator. And if you recall, there's a multiplicity of 2. So here's a fun fact. If I were to ask you where the limit of -1, 2, 3, 4, 5, 6, 7 is, if I were to ask you what the limit of -7 is, since this guy at -7 is going up and this guy's going down, there is no limit. The limit does not exist. Mean girls. However, whenever you have a multiplicity of an even number, my graph goes in the same exact direction on both sides. So when it asks me to find the limit as x approaches 4, since the left side is going up and since the right side is going up, they're both going up to positive infinity, which means the limit of regular 4 is going to be positive infinity. Oh, great, infinity. Well, this hopefully covers those 4 sections. A couple hiccups along the way, a couple stutters along the way, but again, I'm a math teacher. Don't expect me to speak good. Thanks for watching. Don't forget to like and subscribe, and I love you so very much. Bye.